Okay, good afternoon, everyone. How did the practice problem go? Do you have any questions about those before we start?
Yeah, I had a really quick question.
Sure, go ahead.
Let me see if I can find it. It was about, it was actually one of like the first problems. I was just confused. I know we kind of went over it.
Yeah.
It was 1C. 5 is neither even nor prime. I think I just got a little mixed up with the nor part of it.
I thought you're talking about combinatorics. I was just listening. Neither nor, it means not and not.
Okay.
All right, that's what it means.
Okay.
Shall I write it down or you followed? Neither P, let us say, nor Q means not P and not Q. All right?
Okay, yeah, thank you.
Sure. Now back, any questions about the practice problem I gave you? Chris, 4.4, number 16. Okay, we do that. All right, so let's look at the problem and then proceed. So 4.4. So I'll read it and you go back to it. So 16 tells me, how many 4 permutations are there of the set A, B, C, D, E, F if whenever A appears in the permutation, it's followed by E? So I read it one more time and then you guys tell me how to do that. So how many 4 permutation we have of the letters here? So it's a permutation, it means basically it's a list. So permutation, it means a list of 4 numbers where there is no repetition. That's what the permutation of those. If whenever A appears, it's followed by E. All right, ideas. So list, whenever A appears, there should be an E after it. So how shall I do this problem? Anybody attempted the problem? Anybody wants to pitch in, even if they didn't attempt the problem? How would you think about it? Treat AE as one symbol of length 2. Okay. And then, so we can do that. Okay, so I can do that. Okay, so Peter is suggesting that we treat AE as one symbol. Okay, and then we have 4 permutation. So basically we have a 4 permutation. It means we have a list of 4 numbers. And he wants me to treat AE as one symbol. All right, keep going. I mean, what do you want me to do now? So how can I find in how many ways I can have those permutations so that whenever A appears, it will be followed by E. And my letters are, my permutation are from this set, A, B, C, D, E, F. Okay, so of links 2. So 5 symbol of links 1 and 1 symbol of links 2. Peter, can you talk? It's 4 permutation. Be careful. 4 permutation, it means list, an ordered list of 4 numbers. That's a 4 permutation. Okay, so 4 permutation means an ordered list of 4 numbers. It's not all of them. It's not permutation of the whole set. So 4 permutation, it means ordered list of 4 numbers. So how are we going to do this? Anybody else?
Hello, is my mic working? Hello, hello.
And where I hear you.
Okay. Just the way I started thinking about it. So I have, since it's a 4-point permutation and E follows A, I have one case where A is in the first position, E follows it. Then I have another permutation where A is in the second position and E follows it. And then a third where A is in the third position, E follows it. And then there's an individual case where it's AE, because repetition's allowed. So there's another A. I don't know.
No, repetition is not allowed. That's
it's not allowed. Oh, okay.
Permutation. Be careful.
That's right. Okay, so I have those cases, and from there, if repetition's not allowed, then you would just do. You have 4 possible choices in the remaining 2 positions for each one. So it'd be
Right,
4 squared plus 4 squared plus 4 squared.
Right. So 4 squared. So he's just breaking up the problem. I mean, breaking up the problem depending on the position. If A. So if A is here, E has to follow. So I have 4 choices for this. Sorry. 3 choices because things cannot repeat.
Oh, that's right. Yeah.
That's okay. No problem. I did the same mistake. So you're excused. 4, 3, 12, 4, 3, 12. Are we missing any case? Are we missing anything? They say whenever A appears, it should be followed by E. Case with no A, absolutely correct. So these are the cases with A. And then, so let me put them in red. So those are the cases with A, but they say whenever it appears. So what if K does not appear? Case with no A. Okay, so now the second piece will be the cases with no A. So with no A, 1, 2, 3, 4, 5, sorry. 1, 2, 3, 4. So how many situations we have? There is no A, so I'm left with 1, 2, 3, 4, 5. It's a permutation of 4 permutation out of a set of 5 elements. So I have 5 choices for this, 4 choices, 3 choices, and 2 choices. Okay, so we have to break the problem into case with A and case without A. So now the total number is. So is the cardinality of all lists with no A, and those definitely as disjoint. Nothing here basically intersect. There is no overlap between all my cases. Plus the cardinality of all lists with A followed by E. Followed by E. So I broke my problem into disjoint situation, okay? With no A, that's a 5 by 4 by 3 by 2. Or if we use the word permutation, it is in this case that we have a 4 permutation out of a set of 4 elements. The other one is just a sum of stuff. So it's going to be 3 times 12. Plus 3 times 12. And now we just compute everyone and we got the final answer. All right, so we had really to break this problem into pieces to be able to actually control the whole scenario. And we have to make sure nothing overlap. That's crucial. And definitely nothing overlap. If A is here, I'm not allowing A because there is no repetition. So, and the same here. So I don't have overlap in the cases because there is no repetition. Otherwise, this problem will become harder than that. Okay, any other question before we move on? Okay, so today we keep, of course, along the same line. And today we're gonna drop the order. We're gonna consider situation where the order does not really interfere. So combination or counting subset. The book is calling it counting subset, and a lot of other books actually call the idea of combination. So I started this last time, but of course we're gonna repeat. So suppose I have a set S that consists of A, B, C, D. And the question is how many ordered lists of length 3 or how many 3 permutation can we make out of the element of S? So 3 permutation, it means an ordered list of length 3. So we just did that a minute ago. So length 3, 1, 2, 3. And then here we have 4 cases for the first. I have 3 for the second, and I have 2, and that's it. Okay, so that we have 4, we have 3, and we have 2. And here, as we said, for example, if I pick A, B, C is one scenario, and CBA is a totally different scenario. So when I am counting here, that's one scenario and that's another scenario. So the order in which I am listing is crucial. Now, if I tweak this problem and I ask, let S be the same set, how many subset of 3 elements can we make out of the element of S? And now in this case, it's a subset, the order doesn't matter. So how many subset? I can actually compute them easily. ABC is 1. ABD is 1. So subset. So the order is really totally broken. Now I don't care about it. And then of course BCD. And finally the last one should be ACD. So those are the only subset and the numbers of them. The number is, there are 4 subsets. Okay, so it's a very different problem. While here it's a list, it's an ordered list. This is just more than subset. Remember bracket, I care about subset, right?
Can you move the paper up so I could see the first question?
The first one?
Yes.
Yeah, the first one is what we did a minute ago. How many 3 permutation? Permutation means how many ordered list of length 3. Repetition not allowed in this case, with no repetition. Okay, with no repetition is crucial because permutation, we're not allowing repetition. So I should have written this, my mistake. Okay, with no repetition. All right, can I move on? Very good.
Yes.
So example number 2 is basically rephrasing what I did a minute ago. Suppose I ask you how many committee of 3 students can we make out of a group of 4 students? Am I asking the same question as this one? Is it the same question basically? What do you think? Yes or no? If you don't answer, it means you don't think it's actually the same question. So how many committee of 3 students can we make out of a group of 4 students? So basically now what I have in mind is I have 4 students. You can call them what you want. A for Arnold, for example, B for Bob, C for whatever, C for Kathy, and A, B, C, D, and D for Devin. Okay, so these are my students. And how many committees can I make made out of different students is basically the same thing as asking how many subset of 3 elements can we make out of a set of 4 elements, because each subset corresponds to 1 committee. So asking how many committee can I make out of that is basically I'm asking you how many subsets. So when I pick A, B, C, it means I'm picking Arnold, Bob, and Kathy with a C. If I pick A, C, D, Of course, the scenario is understood. Okay, so asking again, how many committees I can choose out of 4? It's like asking how many subsets we can choose out of 4. Or in how many, another way we can ask this question. So I'm repeating the same idea, but different format. Another way I can ask that, I tell you, in how many ways can we choose 3 students out of 4? In how many ways can we choose 3 students out of 4? Is exactly like asking you, in how many ways can we pick a subset of 3 elements out of a set of 4 elements? So it's different format that we ask correlate the same questions. Basically, it boils down to asking how many subsets can we make out of this set. That's why the section is called counting subsets. Can I move on? So now let us start introduce some notation. Okay. Suppose I have a set S, and this set have n element. The cases we took, our set had 4 elements. And k an integer, which is positive and less than the total number of set. Then we're gonna denote by this combination, parenthesis nk, or C and K. And the C stands for combination. C stands for combination. So we use this notation to mean the number of subsets of K elements out of a set of n elements. So this represents the number of subsets of K element out of a set of n elements. Another way to think about it is, nk represents the number of ways we can choose K distinct element out of a set of n elements. So I'm repeating the same idea because that's what we represent. So this tells me the number of ways I have a set of n, and how many ways can I pick? Can I pick K element out of them? And this symbol here is usually called n choose K, which means we're choosing K element out of a set of n elements. So nk represent the number of ways we can choose K out of n. So based on our previous example, in how many ways can I pick 3 subsets out of a set of 4 is equal to 4, because when I just sit down and listed them, I get exactly 4. 1, 2, 3, 4. So we give a symbol for that, and this is called 4 choose 3. 4 choose 3. Since I have 4 sets, I'm picking 3 out of them. And the goal today is really basically understand this, understand where is this formula coming from, and work a lot of problems where this formula is used tremendously, right? If I move and you're not done, you let me know. Are you with me? Can I move? Yes? No? Okay, I move. So, what does 125 between parentheses mean? So that's represent the number of subset of 25 elements out of a set of 100. Of 100 elements. That's really what represent. Another way to think about it, in how many ways I can choose 25 elements distinct out of a set of 100. The elements are distinct because we're talking about subset. In how many ways I can choose 25 distinct elements out of a set of 100? And the question is how to compute that. That's really the question, right? So to be able to compute it, or give you the formula for it, I'm gonna take you back and I'm gonna find the relationship between the number of permutation, because we know the formula for that, and what we call sometimes the number of combination, or the number of subset of K element. And we wanna derive a formula. So to understand, we have to find the relationship. What is the relationship between those? So P and K, it means we're taking permutation. So now I want you to do, we're gonna do the following. So the picture become clear. I want to list all the subset with 3 elements. Now we're gonna list all the 3 permutations and see the relationship between those. So let's do that. Okay. So I'm gonna list all the subset. And then after that, all the permutations. So I'm starting with subset, subset, subset. Subset. No, I'm done with the B, C, D. So those are all the subset, or sometimes you call them, sometimes those are called 3 combination. They're called either subset of 3 elements. In other words, they're called 3 combination. Now I'm gonna list all the permutation. Okay, and then I'm gonna ask you, what's the relationship? Every permutation has to contain 3 elements because it's list of link 3. So suppose I take all the permutations that contain ABC. How many of those are there? So these are the subset. Now here, I'm gonna list the permutation. Permutation. Every permutation has to have 3. So if I take all the permutations that have ABC, how many of them are there? Back to you. Remember, permutation, 3 permutation, it means they have to contain ABC. I'm going to take all those that contain those letters. How many of those there are? Permutation, I care about the order. So I'll have A, B, C. I will have A, C, B. We know how many there are. I can have, started with A, I can have C, A, B. I can have C, B, A. Sorry, that should be in uppercase. Okay, B, C, A, B, A, C. So to every subset, how many permutations there are that use only the element of the subset? We know how many there are. There are 3 factorial of them because we have 3 elements. To this one, how many 3 permutations there are? I can use the same logic. There are 3 factorial of them because I'm taking permutation of 3 elements. How many permutation of this there are? Also 3 factorial. How many permutation there are? 3 factorial. So any permutation you give me from the set A, B, C, D, any permutation should be either here or here or here or here because it contains 3 elements. If it contains B, C, D, it's one of those that correspond to B, C, D. What does it mean? What does it mean? What's the relationship now between the number of subset and the number of permutation? To every subset, there are 3 factorial permutation. To every subset, there are 3 factorial permutation. To every subset, 3 factorial. So what kind of relationship exists between the number of permutation and the number of subset? Can anybody see any relationship between them? Using this example, I don't want anything else. What's the relationship? Subset, permutation. Every subset, I have 3 factorial permutations. So what's going to be the relationship? Anybody has any intuition? Using this example, I don't want anything else. I'm listening.
The total permutations are going to be equal. The number of permutations within each subset times the
I lost you.
Subsets?
I lost you. Can you repeat? So the number of permutations should be equal to how much in terms of the number of subsets? It's going to be 3 factorial times the number of subset. That's the relationship. Does it make any sense? Every subset, there are 3 factorial permutations. So every subset, there is 3 factorial permutation. So the number of permutation is the number of subset times the 3 factorial. Where is the 3 factorial comes from? Because if you take any subset that have 3 elements, so the number of permutation corresponding to it has to be 3 factorial. So that's the relationship between the permutation and the number of subset, because to each subset, basically, the idea is that the multiplication to each subset correspond 3 factorial permutation. And all the permutations are obtained this way. So that's the relationship between them. Okay, I'm going to try to generalize this in a whole. What's really the general relationship between permutation and combination? Okay, once we derive the formula, the rest will be example, but we have to find the formula. So in general, suppose S is a set, and the cardinality of S is equal to N. So what is the NK? Let's see. To each, that's the logic, to each subset of K element correspond K factorial permutation formed by the element of this subset, formed by the element of this subset. I read. Every permutation contains some of the element. Suppose I take a permutation, a K permutation. Every K permutation, the element in it corresponds to a subset. Every subset of K element has K factorial permutation. So this tells me that the number of permutation is K factorial times the number of subsets. The number of permutation is K factorial times the number of subset. And this is going to help us figure out the number of subset. It means the number of subset is equal to the number of permutation divided by K factorial. But what's the number of permutation? The number of permutation is N factorial over N minus K factorial, the whole thing divided by K factorial. So the number of permutation is going to be equal, sorry, the number of subset is N factorial over K factorial N minus K factorial. And that's how the formula is derived, because we were able to derive the formula for the permutation, and now we're deriving the formula for the number of subset. So the idea is that, that's the idea. Every subset corresponds to K factorial permutation. So the number of permutation is K factorial times the number of subset. And this will help me to find a formula that should be totally, absolutely memorized. So now what we're going to do is basically lots of problems to clarify this idea. So I start with a fairly simple one to get the ball going. Okay, question number 8. How many subsets of 3 elements can we make out of a set of 8 elements? So you know, have a set, it has 8 elements. How many subsets of 3 elements can we make? So basically, that's a straightforward question. So it means I need the number of subsets. Basically, I need to know in how many ways I can choose 3 elements out of a set of 8. And the elements are distinct. So that's really what I want. So based on our formula, this is equal to 8 factorial divided by 3 factorial times 8 minus 3 factorial. And we're going to compute this because we have to develop also flexibility with factorial. So that's 8 factorial over 3 factorial times 5 factorial. Okay, let us evaluate this without a calculator because calculators can do that easily. So without a calculator, let us simplify that. Okay, what's the easiest way to simplify this? I don't know. If I'm doing it, I have 5 factorial. I'll break up the 8 factorial this way. I break it up into 8 times 6 times 7 times 8. Okay, I'm breaking it up. And this will give me 3 factorial times 5 factorial. Of course, you know why I broke it up, because the 5 and the 5 will simplify. And then the 6 factorial is equal to 6. Those will simplify, giving me 7 times 8, which is 56. So some flexibility with factorial is crucial. Okay, so that's a typical example. I have a set of 8 elements. How many have 3? That's exactly what this symbol really represents. All right. Okay, now question number B. How many subsets of at most 3 elements can we make out of a set of 8 elements? Now I start going back to you, and you want to, how would you do that? So how many subsets of at most 3? Yeah, I give you a minute, of course, or 2 to be able to think through that. Okay. Now Peter is using a different notation. There are tons of notation for that. So what is the logic? We want at most 3 elements. So how are we going to break it up? Remember, we're breaking this. The whole idea now is we know the basic idea we have to break. So we're going to break it into those, at most 3 elements. It means no element plus. Remember, when I put those lines, it means the cardinality. The cardinality of all the subset with no element plus the cardinality of all the subset with 1 element, because I want at most, plus the cardinality of those of all the subset with 2 elements plus the cardinality of all the subset with no element. Sorry, I did that, with 3 elements. Okay, and let us figure each one of them. Now, how many subset has no element? How many subset has 0 element? 1, that's the empty set. So this one, give me 1, because that's the empty set. Plus, how many subset with 1 element? I mean, here we don't really need anything, it's just 8, because the set has 8 elements, so how many subset with only 1? It's 8. We don't really need any fancy idea or whatsoever. Plus, how many subset of 2 elements? Now, back to what we're doing. It means in how many ways I can pick 2 elements out of a set of of 8. So we're breaking up. We're breaking up to have control over the scenario. And finally, at most 3, it means 3 is included. How many subset of that? So if we want to do this problem, we have to break it into no element. Exactly 1, exactly 2, exactly 3. And then the problem will be fixed. Okay. Questions? Please, I would like you to, all of you, I want all of you to start doing your best to work with me. All right, example number 2. Again, the same ideas. All right. A club has 25 members. How many ways are there to choose a committee of 3 members, of distinct members? Okay. So again, it's like I have a set of 25. How many ways can I pick? 3. I just want to pick 3. So that's exactly, I need to choose 3 people out of a set of 25. So this will be equal to 25 factorial divided by 3 factorial times 25 minus 3, 22 factorial. So if you want to simplify a little bit, I may not compute it, but at least we're going to simplify it without a calculator, as I said. Because I have 22 factorial, I will break my 25 into 22 factorial times 23 times 24 times 25. And I divide by 3 factorial times the 22. So I break it so the math will be easy. 22, 22 simplify easily. And then this should give me, now the 3 factor, which is a 6, 6, 4. So it's going to give me 23 times 4 times 25, which is going to give me 100. 100 times that, which give me 2,300. So some of them are nice really to do them, okay? No, Patrick, it's not, that's the second question. Now, what's the second question asking you for? How many ways are there to choose a president, vice president, and secretary? What's the difference between those 2? What's the difference? Why this question is different from the first one? Please speak up. What is it in B that is different than A? I'm listening. Order matters in B. Absolutely. In B, the order in which I pick the people is absolutely important. So even if I have a subset, let me say the members I picked are Mary and Joe. Those are the committee. Mary, Joe, and whatever, what else? And Matthew. Okay, this is a committee. But now when I'm going to start picking them as president and vice president, secretary, the order matters. So if I put Mary as president, Joe as vice president, and Matthew as secretary, that's very different than picking Matthew. Very different than picking Matt as president, Mary as vice president, and Joe as secretary. So in this here, the order in which I'm picking my committee, the order definitely matters. So now how many we have? So president, we have 25 choices. The vice president, we're assuming we're not picking the same person for both positions. We're going to have 24 choices, and the secretary, 23. Okay, so the order matters here, but the order absolutely doesn't matter because you are just picking, you're just choosing 3. Another way to write this is the number of 3 permutation out of a set of 25 elements. And then we just compute those numbers. Okay, so that's crucial in the sense that I don't care about the order, I'm just picking 3, that's it. Here, no, I'm picking them, I'm ordering them. So a choice for Mary Jo Matthew, President, Vice President, Secretary, even though it involved the same people, but the distribution of the jobs is different. So that's making it an absolutely different scenario than in the previous part. Okay, we're gonna, as I said, we're gonna do a lot of problems along the same line. And we're gonna do the following problem. Can you read at all? Can you guys read what I have right here? If not, next time I will write it clearer.
I can read.
No, too small. Very good. So I'm going to write it. You write it here and you want to think about it. So this is it. The Math, CS, and Statistics Department. So let me call it MCSS, whatever, department. So you have a department. In a certain college has 20 math faculty. It has 7 CS faculty and has 4 stat faculty. Okay, so this is the department. All right, Logan, is this better when I'm writing it? Okay, very good. Now my first question is the following. In how many ways can this be done? You would like to choose a committee of 6 people. Okay, that's a scenario. And now I'm going to give you a bunch of scenarios. Okay, the first one is always my easy scenario. In how many ways can this be done? Can this be done? Okay. Right. So that's the department, 20 math, 7 CS, 4 stat. We would like to make a committee of 6 people, you know, from the whole department. In how many ways can this be done? Does this follow the scenario I have? What kind of answer you guys are getting for that? I think I'm going to start asking students because, Logan, would you like to answer? Do you have a, either put your answer on chat or speak it up. Okay, can you write? Anybody else who can talk? Rachel?
Would it be 31 choose 6?
It's 31, choose 6. Is he correct? Because what's the total number here? I have 20 plus 11, so the total is 31. And I just have to choose 6 out of 31. So that's really the number. So now this is, it means it's 31 factorial divided by 6 factorial times 31 minus 6, which will leave me with 25 factorial. And that will compute that number. Okay, so that's still, I am within a very, very typical scenario. Now, question number B. How many of those committees, how many of those committees? There are a lot of them, but I'm interested in those. Of many committees will have. Exactly. Exactly. 4 math faculty and 2 CS. So we don't want stat on this. So I read the question and I want you to think about it. There are a lot of committees. How many of those will have exactly 4 math and exactly 2 CS? Okay, I'll give you a minute to think about it.
Would it?
Okay, please try to put your answer on chat the best way you can, because I have to know whether you're with me or not. Or just speak up.
I forgot the total number of each faculty, but is it?
It's a good point. Yes, it's a good point. We have 20 math. We have 7 CS, and we have 4 stat.
So is it 20 choose 4 times 7 choose 2? I don't know.
Okay, so you're suggesting 20. And times 7 choose 2. Is your classmate correct? So what is the logic? First, we pick the 4 faculty out of the math people. And for every choice, so there are 20, choose 4 committees. There are that many choices for the math people. Okay, we have so many choices. For each choice, and that's really the product rule now. For each one, for each choice, we have 72 choices for the CS. Okay. So by the product rule or the multiplication rule, we have the product. The total number will be just the product. So the total number would be that many choices for math. Every time I pick those 4, I will have that many for the stat. And that would be the product of those. Okay, one more questions along the same lines. It's the same problem, absolutely the same. That's the setting. My question is, how many of those committees? How many of those committees will have at least, how many will have at least 1 stat faculty? Okay, so this is my scenario. And the question is, how many will have 1 statistic faculty? So we have a lot of committee. I want those who at least there is 1. We need 1 stat. How many committees do we have?
Is it just 4 choose 1? That seems wrong though.
Sure. No, why it's wrong though?
Oh no, it just feels wrong.
What?
I said it just feels wrong. The numbers are really big and that's a really small number.
But Yeah, but what else? What's wrong? So the way you're thinking, okay, let us say the name of the stat people are, okay, Joe, Mary, Matt, and I don't know, give me another name, Jerry. Okay?
Oh, wait, it's the product rule. Sorry, it's
Okay, so
it's
you're giving me 4. They're not 4 choices.
20,
If you pick Joe for stat,
it's,
there are hundreds of other cases for the other people.
20, it's 27, choose 5 times 4, choose 1.
Okay, I will put it down and I want comments. Okay, I want comments. Is that very clear? So your suggestion is let's represent the stat faculty. You're multiplying by the left, but by the rest I meant, right? And the other 6, you're gonna pick them from 27?
The 27 remaining.
The 27 remaining. Okay, do you guys agree with him?
Wouldn't you only be picking 5 more, not 6 more?
Oh, I'm sorry. Yes, because we have how many committees? We have 5. Yeah, you're absolutely correct. Do you agree with him? Anybody has any issue, anything of their concern? In this choice, how many stat faculty will be on the committee? This product represents the number of committee with how many stat on them?
So what you're leading is we have to take into account when there's multiple stat
Exactly,
people.
because what's the question here?
Yeah, at least one. So that's just one case of it.
Exactly, so this is exactly 1 stat faculty. Right?
Oh, so would it be 4, choose 4 then?
What?
Or no? No.
Wouldn't
Sorry.
we just be adding where we change the bottom number of each
Right,
relatively?
we have
So
to
it'd be-
add.
Yeah.
We
So it'd be
have to
4.
add how much? Exactly
So when we have 2,
2.
and then I think that, yeah, we only have 2 people in the stats, right?
No,
Or
we
how many? 4
have
people?
4.
Sorry. So we have to do it exactly 3, exactly 4.
Right, exactly. Plus exactly 4. So we're gonna do it, and then somebody has to give me a better way, not a better way, another way. Exactly 3 stat. Exactly, and the word exactly is crucial here for stat. So now we fill in the number. If I want 2 stat, it means I have to pick 2 out of 4, and for every choice, I will have the 27, but then I'm gonna pick 4 out of them. And then here I pick 3, but then the rest would be picked 3 out of the remaining. Now here I pick all of them, so I have 1 choice, but then I have to pick 2 of the others. So that's at least 1 stat faculty. So we have to break it exactly 1, exactly 2, exactly 3, exactly 4. Who can think about a different way to do this problem? This is absolutely correct as long as we set it up correctly. What's another way to do the same problem? I'm letting you think. I mean, I'm stopping so you guys will interact with me. I want you to think complement. I want you to think complement or the subtraction principle.
So we should take the total number of permutations and somehow
Not
divide
permutation.
out the cases.
No, watch, be careful. Those are not permutation, those are combination, because we don't care about the order in which we're picking the members.
Yeah, sorry, I misspoke.
I know, that's okay, but
Yeah.
Keep going now. Keep
So you
going.
should take the total number of possible combinations and
Yes,
divide out the cases where there are no statisticians.
what do you mean divide up the cases? Be very careful. What does he mean?
I need somebody else to finish for me. I can.
Yeah, that's
I
fine.
can
That's fine.
kind
No
of think of what I'm
problem.
thinking
No
about, but-
problem. No problem. Subtract out. Then we have to take away all the committee that have no stat faculty. So let me say it again. Another way to do the problem is think complement. Okay, how can a committee not satisfy this condition?
So I have 31.6 minus 27.6. Is that
I will check you out. I will check you
Okay.
out. Okay. So let me take A to be what I am interested in. All the committees with at least one stat. That's the one I'm interested in. And my universe, all possible committees. That's my universe. Okay. So I'm going to write A, that's my set A, is the universe minus what? So a committee with at least one stat, okay, it's finding those, it's just taking every possible committee, but taking away the committee, what's the complement? The committees with no stat. Okay, that's my set. So it's everything, at least one stat, it means all of them, take away from them all those that have no stat, then I get everything with at least one stat. Okay, so now what's gonna be the cardinality? The number of elements is the universe minus all those with no stat. Because if you remove those with no stat, you're left with those who have at least one stat. With no stat. Okay. So now, total number of committees, we know that it's 31. Pick 6. That's my universe. Those would have no stat. Now I go back to my given. My given is that this whole class had, this whole school had 4 stat faculties. So if I don't want stat, means those has to go, then my choice will be out of the 27. I pick 6 out of 27. Okay, so sometimes thinking complement is a little bit easier. So here, committee with at least one stat. Okay, how can this fail? This fail if the committee has no stat. So I say, okay, fine. So I take everything and I take away from it the committee that doesn't satisfy that, no stat. And then I get this, all right?
Can I see
Go ahead.
I see the other page where it had one part of the solution, because I'm trying to see how we get 6 on there.
This one?
Yes.
Yeah, which part is not very clear?
it's 6 because we're choosing 6 committee members, and the other problem was the total. It's breaking it up here, so that's why the other problem has 6 and these have different numbers. But if you
Okay.
look, the bottoms add to 6 in each case when you add them.
So if I go one by one, this 4-1 represent what? In how many ways? It's exactly one stat faculty. This, in how many ways I can pick one stat out of a group of 4. For every, suppose I picked Joe from stat. For every choice, I have all the other 5 members that I'm going to pick them from the 27 because I don't want stat in this anymore. So for every Joe, I have tons of other cases for the other members. So how many I have? I have 27, 5. Then I move exactly 2 stat. I pick those 2. So now I have my choice of the stat, Joe and Mary. But for every choice of the 2 stats, I have tons for the other ones. I have to choose the 4 other committees, the member out of the 27. I have a lot of choices because I have 27 members. Now I have to choose 4 of them. 4 plus 4, as your classmates were telling us, is 6. Then exactly 3 stat, I pick my 3 stat. I still have 3 to deal with. I pick them out of the 27 left. I have 4 stat. I still have 2 to deal with. I pick them out of the others. Is this making any sense?
Yes.
Okay. In this case, no, I thought about it in a different way, but both are used in different scenarios. Here I thought about it, you know what, why don't I remove from the whole those that have no stat? So the leftover is I have at least 1. And I use the subtraction principle to do it. All right? Okay. Let's do more problems. I mean, of course, the idea here is once we slowly we get the idea and then we start working with it. So I will write the problems because my paper is not clear at all. Let me write it. First, what's a binary string? A binary string is a string that consists of 0s and 1. So a binary string, let us say of length 7, is a string that consists of 0s and 1. Of 0s and 1. Okay, so a typical binary string is of length 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, something like that. 0, 1, 1, 0. That's what's a binary string. So my first question is, of course, the easy one always, how many binary string of length 7 we have? So how many binary string of length 7 can we make? Okay. All right. Is this an easy or a hard problem? Okay. What's the answer to that one? Please type the answer. Anybody?
So is it 7 choose 2?
No. No. It's something we've done
Or
a lot.
is it,
We're not picking this time. We're not choosing.
It's a permutation.
oh yeah, it's permutation. Yeah.
Wow, it's not even permutation. Permutation, there is no repetition.
Oh, 2 to the
It's 2 to
7.
the 7th.
Sorry.
Yeah, order
Exactly,
doesn't
exactly,
matter.
exactly. It's 2 to the 7 because now always try to don't get those ideas confused. 1, 2, 3, 4, 5, 6, 7. It's not a permutation because there is a lot of repetition. I have 2 choices for that. For everyone, that's a 3. 2 choices, 2 choices. So that's 2 to the 7. Okay, please be very, very careful not to confuse ideas. And that's 3. So we pick the first one is, we have 2 choices for the first. For every one, I have 2. Let's make it 4. For every one, I have 2. Let's make it 2 to the power 3. And that's really how this picture goes. B, how many binary string of length 7 can we make that have exactly 4 ones? So I will write it. How many? Binary string of length 7 have exactly 4 ones. So what's in my mind? Something like that. 1, 2, 3, 4, 5, 6, 7. I want 4 ones. Exactly. So the rest will have to be 0. So that's really one scenario. That's the scenario I am interested in. How many of those strings of length 7 have exactly 4 ones? Okay, I will let you interact with the problems before I take it on. Two to the power 4. On what basis? 2 to the power 4, it means in my mind we have 4 things, and I'm picking 2 for this, 2 for that, 2 for that, 2 for that.
Sorry, I think I understand what the answer is like based on, but I can't remember how to calculate it. Is it the number of ways to position the 4 elements in 7 positions times 2 to the power 3?
I don't know where the 2 to the power 3 comes from.
Or would it be I was the 3 remaining spaces times the 2 options for each of them?
Okay, anybody else? I want everybody to think about it a little bit, and then I will try to comment on your classmate. He's half correct. Okay. So let's call this position 1, if you want. We're going to call this position 2. Position, it means that's what it is. Position 3, position 4, position 5, position 6, position 7. So those are position. So let us say I take my scenario here. So before you really...
Oh, there are
okay.
exactly 4. Sorry, I'm dumb.
That's okay, no problem. Okay, let us take this scenario. In what position are my 1? They are in position 1, position 2, I meant 3, position 4, so 1, 2, 3, 4, 5, and position 1, 2, 3, 4, 5, 6, and position 6. So if my 1s are located this way, they are in position 1, position 3, position 5, position 6. Suppose my 1s, so I'm just giving you examples, so see my 1s are here. 1, 1, 1, 2, 3, 4, 5, 6, so 0, 0, and 0. Okay. If my 1s are in here, it means which positions are they? Position 1, position 2, position 5, and position 6. Okay, so to every position of the 1s, I can basically associate a subset where the subset represent where the position of my ones is. So for example, suppose I have this subset of we have 7 positions. Suppose I take this subset, 0, 4, 6, 7. What position I have in my mind? 1, 2, 3, 4, 5, 6, 7. I have the position, 2nd position, 4th position, 6th position, and 7th position. It means that's really what I have in mind. Okay, so every time I put those my 4s, I can associate to it a subset of 1, 7, where the subset represent in which position. So this is the position, position 1, position 2, position 5, and position 6. Okay.
So would the answer be 2 to the 3 for the remaining slots that aren't the remaining positions that aren't taken up times the amount of subsets we can form the ones?
It's the amount of subset, but I don't know where the 2.3 is still coming from.
Well, wouldn't that be the remaining? Where the zero? Where
But
the?
they are-
Oh, exactly,
It's exactly
Yeah,
4.
you're right. You're right. You're
Exactly
right. Okay.
4. So the others
so it
are
can't-
what?
Yeah. It
The
has to
others
be
are a
0
bunch of
though.
zeros.
Yeah.
Okay, so the number of positions where the ones are is the same as the number of subsets. The number of subset of 4 elements, because we have exactly 4 out of a set of 7 elements. Okay, in this particular scenario. So the number of positions of those exactly 4 ones, exactly 4, is the same as the number of subset of 4 elements out of a set of 7 elements, because to every subset I can associate a position. So the number of string is, and now I will comment on everything you guys were saying, is going to be,
Is it 7 choose 4?
7 choose 4. But now let me explain clearly. It means once I pick my position, so there are 4 ways to position the ones. Once I position the ones, for every fixed position of the one, in how many ways I can position the rest? Multiple ways? In this particular scenario, or 1 way. Once I position the ones, I only have zeros because I have exactly 4 ones. So once my ones are there, I fill the rest with the zeros. I don't have a lot of other cases in this scenario. So the number is going to be exactly the number of ways I can pick subset of 4 elements out of a set of 7 elements. So because every subset gives me the position. That's the way we're thinking about those problems. Yeah, it's fixed 1 way, exactly. All right, and exactly is crucial. Exactly for ones, it's crucial, or the problem will not be actually as simple as that. Yeah. Now, if I don't have much time, but let us say, which was the last problem I was planning to do with you, but along the same line, let us say now I want to make string of, let us say, link 7 out of, actually I will give it to you as a homework also, as a practice, not homework, out of the letter ABC, not binary anymore, not binary. So now I'm going to allow the letter ABC, and repetition is allowed. So let's be very clear, repetition allowed. So I'm thinking about 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. And I'm having numbers like I can put A, I play around, B, C, C, A, C. This is what we mean by string. Okay, let us say I ask you this time, how many contain exactly, and the word exactly for now is crucial. Let's 2 A's. Okay. So this is my scenario. And how many contain exactly 2 A's? So 1, 2, 3, 4, 5, 6, 7. I want 2 A's. That's what I want. And the rest are the B's and the C's. So how do we think about this problem?
Is there a way we can consider it where it's like, so for the last one, since it was binary, we just stopped at 7 choose 4. But if we do 7 choose 2 and then another 7 choose 2, it'd just be where it's A's and B's and then A's and C's. Does that make sense? I don't know.
You have to, I don't want you to guess, right?
No, it's not a guess. I don't know if that makes sense, because like if you treat it where it's almost like 2 different binary problems where it's A and C and A and B.
Mhm.
Does that logic make sense?
No.
Okay.
No, I want you to think about this one problem. Let us think about that. First, in how many ways can you fix, can you position the A's? You gotta think about it very logically. Number of ways to position the A's.
So 2 choose 7 choose 2.
Yeah,
Yes.
it's the same as last problem with the positioning. Now it's 2. So that gives you your positioning.
Do you understand, everyone? Do you guys understand how I'm getting this from? Because I have 7 position, I can put 1, 2. Let's consider subset 1, 2. I can put them 1, 3. I can put them 1, 4. I can put them 2, 3. So I'm really after the number of subset of 2 elements out of a set of 7. And now that's how we think. Once we fix the A's, so there are set many ways to position them. Fix one position. So when we fix one position, I know how many we have. I fix one position. In how many ways can I fill the rest? Now this is the string. Now I want you all to think. Those are fixed. In how many ways now I can make string?
5 factorial over 2 factorial.
You're still guessing. I want you to think. My A's are here. I still have 2 letters to play with. Right.
It's just 2 in each slot, 2 choices in each spot.
I have
so
2
2 to the
choices.
5th.
I have 2 choices. I have 2 choices, 2 choices, 2 choices. So once I position my A, I said, okay, this is my problem now. I don't have to worry about those anymore. In how many ways can I put the B's and the C's? I have 2 play because repetition is allowed 2 times 2 times 2 times 2. We have, so for fixed with position, we have 2 to the power 5 ways once we fix the position to put the B's and the C's. So the total number now is going to be the product. Okay, that's how many ways to fix the A's. For each one of them, I have 2 to the power 5 ways to fix the other ones. And that would be the total. Okay, so don't try to think about it logically. How many to fix the A's? You fix them. Then you ask, okay, how many ways can I fill the rest? I have lots of choices. I can have B, 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 B. I have C, 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 C. I can have B, B, C, B, C, C. There are tons of them. And how many? Repetition is allowed. Otherwise, the problem doesn't make sense. I have 3 letters. I have a string of 7 length. So I have to force repetition. So the total is going to be this way. All right? So for next time, because we have to quit, I'm going to put the problems that I still wanted to do today. I will put it on Brightspace for you, and I'll give you some practice problems from the book. Please, look them over, and we can discuss them next time. right? And as you know, your homework is on Blackboard. It's due someday, I think. Yeah. Right? Any question before we go? I quit. All right, bye-bye, guys. Thanks.